All right, happy Thursday afternoon. We're going to get some construction noise there today, but that's all right. The topic today is we dig a little bit deeper into this AMOC business, is the conceptual idea of tipping points. The tipping points idea will have applications beyond AMOC, but it is a good example thereof, one. And several of you pointed that out in the articles you found. Well, most of you found similar articles that all stem from the same science report that's a couple of years old. And that was a good example of AMOC flipping, and we'll talk about that a little bit later. So we're gonna go deeper into the tipping points. One of the things that, before we get too far into that, I'd like to spend, what we haven't been doing, and probably I didn't think it was necessary, but I wanna spend a little more time going over the homeworks in general to explain sort of one or two of the areas that we had a little bit of trouble with. So we're going to do that first. And the basic diagram that was put out for you to interpret is this one here, which tells us the relationship between three things: temperature, salinity, and therefore the resulting density of seawater. And this is a theoretical model of that, and there's curved relationships here for reasons that I can't fully explain. But it's an empirical relationship that we can use. So I was doing two things with the homework exercise. I was saying, oh, here's some real data. And read that graph and then compare it to what the theory comes out to be. Some of us did that fine, some of them were a little rough. By dumb luck, more than anything else, the area that we showed from the Irminger Sea, the data set that I had the time series of for 3 years, had a density that plotted right about where this Red Sea is. And that was not by design. So basically, this was a representation of the temperature and the salinity conditions from that data set. There was a little bit of glitches. There's a little glitch with the units. These are the same number, the decimal point changes on. But because that set of conditions did that, part of the trick was the salinity didn't change very much. It changed subtly, but it didn't change much when you looked at it in detail. What changed, obviously, was the temperature. Most of us, we had some glitches getting it. That was the fact that we have seasons, and therefore the sun's rays at high latitudes in what we call the Northern Hemisphere summer beat down on places like the Irminger Sea, both for a longer time during the day and with more intensity. So there's more energy for actually two reasons. That's what sets the rest of the clock in motion. That energy balance warms up the ocean, and that is why we have the distinct annual cycle. The salinity, there's a little bit of a glitch to it, but it doesn't necessarily make the big game. So if you take the average of all of those measurements, which is this number, here's where you would start plotting that the salinity stays the same. You could have taken a range of these numbers because we had high temperatures that were sort of like this for the highest part of the summer, and then the lows were about 4 degrees. And 4 degrees turns out to be a magic number for water. That's where it's pure water. Its maximum density is always taken as 1 cubic centimeter or gram per cubic centimeter. That's the density of it by definition. It's an operational definition. But it's always specified that it's at 4 degrees. Why? It turns out water is bizarre in the sense that when it gets colder than 4 degrees, because it's starting to get ready to freeze, it starts getting less dense again. Ice floats. So the liquid water is one of those strange materials where the solid phase floats on the liquid phase, less dense. And that has actually a lot of implications, particularly about sea ice. But be that as it may, this diagram was what we wanted to work with. The second thing was, okay, we've got a body of water. It's 30 feet deep, so it's not really exposed to the atmosphere, but obviously it was modulated by that temperature range. And we looked at 180 meters deep, and we said, well, what's its density? And when you plot up those conditions, you get the red dot. And it's more dense, and so that leads to the fact that under the present conditions, this is less dense than this, it's not going to overturn. the conditions you saw there, it doesn't matter how cold it got, it could even get down to 4 degrees, or the coldest, it wouldn't bring it down enough to get it this dense. Because the salinity didn't change much. And the colder temperature is not gonna bring it down far enough to make it flip, to get the density high enough to intrude on this body of water. So the idea though is that you could, one of the take-home messages of all this is that you can get from here to here by a couple different ways. One, you could just change the salinity. If you want to just change the salinity, you're going to jack it way up. Or you could just change the temperature, and it's getting close. If it turns ice, it's going to, all bets are off. But you could just change that. Or you could have some field of the two. You could bring the temperature down to here, and then you'd have to bring the salinity up to here in order to make it work. So that's, I mean, there's a little bit of trick to that, but I think we're in pretty good shape. But I wanted to clarify it because there was enough of us that ran afoul of that. Anything I could answer for questions about this diagram? I kind of asked it the same way a couple times. We got a sense of the density is important again. Ready for new stuff? Looks that way, let's do it. Well, it's not new stuff, it's the operational definition of AMOC. Now we know that it's not a simple thing. Remember to see the spot that we looked at right here, which isn't exactly in the Gulf Stream, but lo and behold, this dashed line tells us that it's doing its overturning. At least this branch of it is. There's another branch that goes up into here and goes into the Arctic, and that suffers a different fate. But someplace in here is where the actual overturning takes place. Now, the data we had didn't indicate that it was happening. And there was another data set from even deeper in the water, which it was quite a bit more dense. That's some of this colder water coming in from here. Cold, salty water coming in from the Arctic. That's all fine. But we now see that there's the ability to have an overturning. The homework exercise for today is a graphical illustration of this. I'm going to ask you to look at both the surface temperature and the salinity as we go from about here in the north-south direction down to closer to the equator. And we want to see as that water migrates up, you see it keeps changing color here. And we're going to talk about why does it change color. There's two basic reasons it changes color. One, it gets colder because it gives up the heat. And then the second, the sea ice business. What's the sea ice? It freezes and sticks the salt water in here. And the salt water, this happens to be over this, this is about the limit of sea ice. Makes that overturn. So we're going to, it's sort of the same concept, but we're going to figure out what that looks like in 3 dimensions as a homework exercise. It's a graphical. Questions 1, 2, and 3. The other 2 go something else. Blah, blah, blah. This doesn't have all of this detail, but the result is this deeper water as we move. The 8.2, this is all review. Who can tell me what the 8.2 is about? Why do we care about that? In the geologic past, it happened 8,200 years ago. Who cares?
I have that it caused a rather large influx of fresh water and it had rapid impact on recovery for a few hundred years.
So the idea is that there's a concept here about this overturning, and it's overturning, but something geologically, which is a kind of unique experience actually, happened, and it blurped out a bunch of fresh, cold water. And so that density changed. And we'll see in the next graph, and we've seen some other graphs where the climate changed. Now, last part of what she said is that we were able to upset that balance, but as more water came in, the balance reestablished itself. These things have an awful lot of inertia. They're big, they're slow, they don't take kindly to perturbations. Many of you found an article about a technical paper that is going to make the argument that if we melt a lot of Greenland, we can do the equivalent of this kind of freshwater forcing right at the same place. The understanding of that physics is far more advanced when we recognize this happened in the past. Whether you can generate quite that amount of water, I personally have a little skepticism, but it doesn't matter if I have it or not. It's the same exact principle. So what would be a take-home lesson from this particular exercise? Applying it to the future. No?
I don't know.
What would be something we could be gleaning? We're talking about potentially, for a slightly different reason, but the same problem, shutting down the AMOC, right?
Yeah, what's the question?
Why do we care about that?
Oh, because it would reverse the flow of the water, which would have very rapid and drastic effects on the weather cycles, and we wouldn't be prepared for that.
So the events that happened last time, or in 8,200 years ago, could be replicated in the future for an entirely different reason. One got cold water, catastrophic mechanical. Another is you make a lot of fresh water because you're melting ice. And that effect, the ocean doesn't care what the cold water comes from. It might. And the papers that the root science papers that most of you found the public press for suggest that could happen sort of in the next 50 years or in your life scale. So ultimately we want to think about what happened. I'm still talking about the mechanisms that's happening here, so you'll have a full understanding. On Tuesday, we'll dig deeper into so what happened. Was it a big deal or wasn't it? All right, so that's a review. We've talked about why we're doing this again. Here's yet a different graph than you saw the other day of things, and you can call this temperature. Now this is a lot finer scale. This is only a couple degrees of temperature. But this is the present time. This is 10 or 11,000 years ago. We came out of the ice age. Oh, that happens to be warm and fast. It gets its own lesson. We went through some variations over time, but the biggest variation in the last 10,000 years is this drop at the 8,200 Kelvin. And it's basically expressed as a cold through most of the places. So one of the questions we might ask, if we do it for a different reason, but it shuts the circulation off, then is that going to give us a cold event in the future? Don't know. It's going to be disruptive, but maybe it is cold, so maybe it's okay. We'll cool things off. And then we've looked at the distribution of this. It's going to disrupt things in the Atlantic more than it's going to disrupt things over here, say, in Southwest Pacific. Okay, whole new topic. I want to stand back and be abstract about systems. Systems are some combination of inner working parts. We've talked about the atmospheric system. We're now talking about the ocean system. We could talk about the combined system. It's a bunch of parts that interrelate and feed upon each other. When we have feedbacks, we have a system that had linkages where the effects would ripple through and come back to where they started from. If we plot those systems over time, they have certain characteristic shapes and configurations, and that's what I want to expose you to in an abstract sense today, because it applies to 2 or 3 of the systems we're working on. The general thinking is this. We have 2 axes here, and this is our forcing, and this is how the system responds. Doesn't matter what you want to call the system. Go back to the tea kettle on a burner. If I turn up, what's the forcing? The forcing is the heat. What's the response? The temperature of the water. If I turn up the heat, what's going to happen to the temperature of the water?
It's going to increase.
And in this case, how is it going to increase?
It's going to react to the water, or it's going to react to the temperature increasing over time.
They're going to happen, but this system shows me that as I go from here to here, I get this much temperature increase, right? If I go from here to here, do I get the same number?
No.
Same increase. So from here to here, right, goes up that far. From here to here, if I go up that far, it goes up the same amount, hotter temperature. But it's responding in a linear way. So there's kind of a one-to-one relationship. They don't have to be numerically one-to-one, but every time I crank the forcing up, the response is out. The climate sensitivity that we spent the first 3 or 4 days on assumes that there's a one-to-one relationship of CO2 level with the output of temperature. By definition, it is the amount the temperature will go up for doubling of CO2. Change the CO2 effect by, change the greenhouse effect by changing the CO2, and we could get a linear or some simple response to it. And that's what very first lecture I said I think is bunk, and part of the theme of this class is to convince you that that's not true of the climate system. This could be true of how much work you put in the class in your grade, but I don't think it has anything to do with the climate system. Okay. So, this one's not quite the same thing. So this is, I'm putting a specific response on it, the water, the temperature, and then the flame size. What's the description of this one, the gentleman in the black shirt, t-shirt? Describe what the response looks like, please.
As the flame size goes down, the water temperature also goes down.
So you would have to, if you had to put numbers on this, and let's say it's, 1 inch high, 2 inches high, 3 inches high, whatever, you would say that this has to be a flame size getting smaller as we go. Not what we probably think of it as the flame size going up, right? Yeah. Is there any way though that maybe that this is not as simple, that the flame size might not be as simple as what we would expect it to be? Water temperature goes down because the flame size gets bigger. Not clear that you could get an example, right? So we'll live with it for now. So this is a simple system, simple linear responding system. Another type of system that's more common in the real world, in the black body radiation that we talked about in the first or second day, is one of these, is the forcing and the response. I put more energy into the black body, it emitted more radiation as a response to that. And it wasn't a one-to-one because it was to the 4th power. So this is a thing where I go a little bit, and it goes up this much. But over here, I go that same little bit, and it takes off. There are very few things that have an exponent to the 4th. There are a lot of things that have an exponent to the 2. So an example here, then, of a responding exponential system enforcing was the black body radiation. Can you think of another one? Another one. A responding system where things keep changing.
Like the sea ice melting?
Excuse me?
Like the sea ice melting?
Still didn't hear you, sorry.
Like the sea ice melting?
Okay, so the sea ice, we wonder what would be the axis, the sea ice melt, the size of the sea ice or the area of the sea ice?
The size?
We have to have a property, the forcing has to have some sort of property, so size might be a reasonable one, okay? So size of sea ice, what's this then? It doesn't have to go up too, it could go down. So if I more or less sea ice, what am I controlling? Well, in a roundabout way. That's the one that had the albedo and it bounced the energy off. So that's maybe not quite the best example of this. That's probably more linear. In other words, if I change the sea ice size, the amount of energy that's either bounced off or goes into the ocean is kind of related to the size. It would be more linear. It wouldn't be a straight line. It might be a different slope. But I don't think that, it wouldn't be that the smaller and smaller I got, all of a sudden it's going to take off. Okay, so another possible thing that might have sort of an exponent, not similar response, but some sort of linear response, suggestions? Anything, I don't care, it doesn't have to be climate related.
Exponential? One that's exponential?
By definition, most of these relationships are described with exponentials. So what are some of the things that might have an exponential in them? That's a tricky one, because we're not really familiar with a lot of things, the math behind them, right? Okay, so, but one of them is compounded interest. Your value of this thing theoretically takes off. Why does it take off? Because in this case, there's a feedback here. The interest goes up a little bit. The next time though, there's more principal. And so the amount that it goes up, even though you got the same interest rate, goes higher. And so the next time that you get your interest, the next year or whatever, up it goes, and then eventually it can take off. You can get quite a lot of return on your investment because the interest keeps compounding. And that's the argument that stocks make in order to, increase your wealth. Okay, so exponential, there are systems that have an exponential decay. We could, and as she suggested, if we looked at the math behind them, look for the exponent. Another one that's less clear would be an oscillating. The gentleman way in back. So what do you think I'm going to talk about oscillating?
Yes, you're talking about a swing.
Well, the swing would be good. Explain to me how a swing works, though.
Well,
Or describe how the system of this.
I mean, a pendulum with no air resistance will just keep swinging back and forth to the same point that it started.
What if I talk about the forcing, though, what's forcing a pendulum? What's making it pendulate, if you would? I don't think that's quite what it is. Gravity.
Yeah.
And so how does that work?
I mean, you get acceleration as you come towards the bottom.
Right.
And at the bottom, you start losing acceleration as you come back up. And
You don't lose the acceleration, the sign changes, because you're getting further away. So you have forcing that will somehow change. But the response, in this case, the forcing changes and the response changes also on a long term, right? And as we described, the swing does this, that there's a push to get the swing going of the pendulum. So we could think of a push and back it comes, a push and back it comes, a push and back it comes. It's going to vacillate between certain limits. It's not going to exceed the limits. The take-home point here is that swing or pendulum is only going to work to a certain range. And the climate system is not necessarily one of those that works within a certain range. For some time scales, it does. The daily temperature. The sun comes up, it gets warmer and warmer, it gets warmer and warmer, the sun goes down, it gets warmer and warmer. There's a slight glitch with this, but I don't think we need to worry about it too much. But there's an oscillating system. A lot of patterns we see in nature have an oscillating like property. They may or may not be exactly oscillating, but they have some rhythm to them. And so that's what I want to take home for that. Questions on that so far? Okay? Forcing and response are related. We could track by time, you usually track it by time. What's the forcing and the response, the magnitude of the response. Okay, so far. Tipping points are different than that in the sense that basically you keep pushing them, you push them, they go in a linear response, and then all of a sudden they jump. So instead of having some simple system, you're pushing it, and you're pushing it, and you're pushing it, and the system might behave, and it might do something, and then all of a sudden, there's a catastrophic break point. Technically, I think they call it a bifurcation point. So our working definition is a critical moment in a complex situation in which a small influence or development produces a larger irreversible change. We added a little heat to the boiling pot of water, we added a little heat, we added just a little more heat and it blew up. Didn't go up 1 degree, it all of a sudden went catastrophic. The system doesn't work that way, but that would be an example of what's going on. So this catastrophic thing, the point, and so that would be that point at which this slow reversible change. Up to this point, the argument would be if you change this value, you could keep it stationary. In other words, if you forced it to this point, it's behaved. Be like what we always talked about. One step over, 1 iota over, click, goes something else. Some other behavior pattern. Becomes irreversible. And then they throw in with consequences depending on the system. So that's a definition of the thing. The analog, the straw that broke the camel's back, the idea that the camel has a certain strength, you keep putting the bales of straw on, or hay or whatever on the back, and all of a sudden it does it, but it doesn't go it forever, it breaks. One little last straw broke the camel's back. And so what would that response look like? Write that in your notes, please. And where have you already seen it? Where have you seen a response like this?
Are you talking about the 8.2?
Perhaps, but so far we're doing these things schematically, right? We're having forcing and responses. We just did it for 3 categories. Now I want to stylize the same conceptual idea. If a system has a tipping point, then it looks like this. Where have you seen that before? Or how would you draw that sketch? You want to try to draw that in your notes to be sure you visualize it. And then I'll talk about it in a minute. But I want you to think about how to represent that before we go on. There's a couple different ways you could do it. It doesn't have to be that the system took off and went up. We're already drawing it up. It could go down or something else. So what is this response in a system that has tipping points? We also called them nonlinear. I also called them chaotic. There's some subtleties in those definitions. For our purposes, they're all kind of the same. Where have we seen one? Where have we seen one already, or have we? Oh, yes, sir.
Would it be that small ice age where there's that dramatic jump?
A little ice age?
I think that was a real one. I might be thinking the wrong event, but in that timeline there was one that spiked up.
Actually, we haven't seen too many great examples of it, but here's some natural oscillations. And we're not going to talk about them. They're going to be responsive, but there's noise in any system. And so the temperature changes 1/2 degree or something, or 1.5 degrees. So all of a sudden, it changed by more. Now, we don't know it's forcing this. We don't have the forcing mechanism yet. This is just the behavior. It's just what it looks like. So is that a catastrophic, or is that a tipping system with a tipping point? Yeah, that's why we've got this as an example. So the fact that in this case, it was a certain amount of water coming in, a certain amount of water, and then all of a sudden flood, a deluge, kicked it over. So that's not necessarily quite the same as a little bit, a little bit, a little bit. But this is what they're advocating for the upcoming. The melting's going on, the melting's going on, the melting's going on. That's a technical term. This one came back. We didn't break it irreversibility for a long period of time. So it doesn't formally fit that definition. We didn't kill off AMOC. We didn't stop it from ever happening again. But if I were going to draw a diagram of that, it would look a lot like this. Catastrophic step function in the behavior. And so I'm going to give you some other examples of these behaviors in these systems. And the step is the key point. Anything beyond that. Okay? Started from a normal state, tipped into a cooler period. Stayed there a couple hundred years, and then there was some feedbacks that allowed it, thermal inertia of thermal halide circulation was enough to kick it back out of that state. And it kicked it out pretty fast, actually. So that's a system that has tipping points. It could have been this, with a little bit more meltwater, it could be that. Okay, so that's why I hinted to search for tipping points, because that's the way we define them. Now, again, another geological example. What we've been looking at most of the time is here's 140,000 years ago, here's today. Here's what we've been looking at. There's the 8.2 event, little thing, but it's a nice spike. If we go back in the Ice Age thing, and we're gonna talk about this spike here later, but pick one color or the other. It's a little confusing with both colors. This is real data. There's a bunch of jumps all the way through here. They're not the jump between the glacial conditions and the non-glacial conditions. They're sort of halfway-ish. But every transition's straight line. Jump in, jump out. Jump in, jump out. Jump in, jump out. The other way to think of it is jump in, jump out. Jump in, jump out. The oscillating system, it's not which is normal and which is the abnormal. Not so simple. It can go either way. I mean, you could start it one way or the other. So these things, these oscillations have a particular name. They have a larger magnitude. They're 3-4 times as big as the 8.2 event. They're called, and they're about a millennium and a half long. Most people associate these days with ocean circulation patterns. If you put a ping pong ball in the ocean and you let it go through the cycle, it takes, guess what, 1,250 years-ish to come back to the same spot. So there's some resonance or there's some frequency in the ocean that's on the right time scale to do this. Details to be announced later, it's still fuzzy because everybody's debating. Point of this, it happens. The technical language behind explaining this is really pretty full of gobbledygook. It's hard to get through all of the words that are in there, and this is the simple summary of this particular paper. But what they're asking is slow and soft passage through a tipping point of the AMOC in a changing climate. They're trying to argue that maybe instead of this thing, this camel's back breaking in one day, it takes a little while. It's still gonna tip, it's still the magnitude of change is gonna take in, but it takes some period of time to do that. So this is kind of a level of sophistication beyond what we necessarily need to understand, but they have some pretty pictures, so that's why I talked to them. So, okay, so they talk about paleo records suggest the AMOC is a threshold for abrupt climate change, what they call abrupt, the so-called tipping point. So these terms have some similar meanings. Abrupt climate change, different from gradual climate change. It has to have a tipping point. Classical bifurcation theory, based on the tipping point dynamics, implicitly assumes a tipping point is fixed. In other words, every time you do this experiment, it's going to break at the same number of straw bales. That's what that sentence is. Bifurcation theory, the fact that it has a tipping point is always going to be the same point. They're going to basically argue time varying forcing exposed to ice meltwater, which is not simple, the actual tipping point can be overshot, and then the system catches up. So we can actually put more water in to do the trick, but we've already committed to the tipping point, we just don't know it. The tipping point has been reached and exceeded, but it will happen later. Okay, the rest of it's kind of for your own information, and guess what, there's the 1,300 years. All right, like I said, and then they talk about Dansgaard-Oshkosh events, which are the thing you just saw. So these things are all related in some way. The pretty diagram is this. let's start with this one. So here's a U-shaped vessel with marble in it. If you put the marble in the vessel, it's gonna come to rest at the bottom of the vessel. Pretty simple. It'll oscillate back and forth. You drop the marble in, it'll go up and down here a few times, and then go down and stop here. In this case, if you take you take a more complicated container, and you put the marble in here, if you just put it in gently, it'll roll up here, and then it will think it's stable, because it is. Locally, it's stable. If, on the other hand, I dropped it a little bit higher up, it would go up over the hump and down to the next level. So you can see that there's, for this marble, depending on how it's started, there's two oscillating phases. One here, or if it escapes that, there's another one over here. It's starting to get hairy. This is sort of what they're trying to get out. And they're saying with increased water, you can do this. I'm talking about it's a neat diagram. It's a way to talk about it. So stable system, vacillate back and forth, quasi, and then maybe quasi at two different states. Let's forget this because they're trying to do something special. But this is, again, time. It's vacillating, the climate system's vacillating, 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 and then the forcing change, and then the actual response comes out. So it could be delayed, and I don't want to get too hung up on the delayed business because this is an experimental idea. The real point is, when you have bifurcation points, computers like to use a math problem, and will calculate a formula, calculate a formula, calculate a formula, calculate a formula. If you have a bifurcation or tipping point in it, there's no simple calculation. There's no math that describes adding one and all of a sudden it goes 20 units different. That conceptual idea is easy to draw, hard to model, difficult to model. None of the computer models that we're using to predict the future at this time have tipping points in them. Questions? With the red, whatever those things are. No questions? Then explain all these tipping points to me. Do you like tipping points? It'd be great if it was in your bank account, I know. Describe what would happen if your bank account or savings account had a tipping point.
One small change, but it can change drastically.
Okay, give me some specifics, please. So you have a balance that goes up and down every month because you get a paycheck and you have expenses and blah, blah, blah. July 2025, a tipping point creeps in. What happens?
Like there's an emergency.
An emergency. All right, your balance just took a hit. And there was no way for you to predict that emergency by definition, but your bank account felt it and recorded it. Do you have another example?
I was gonna say winning the lottery.
Same difference, different sign in the account. Yeah, one goes up, one goes down. So your bank account has this natural ups and downs, and some months you have more in it and less. But all of a sudden you win lottery, or you have to fork out for a broken car differential. I had to do like last fall, so I know exactly how that works. But yeah, it takes a hit. It wasn't an emergency. Okay, let's go. Hysteresis. I'm gonna pass on hysteresis for today. The ocean circulation, AMOC, has a tipping point. One of the things that's less clear is there's many other systems on the surface of the Earth that have tipping points. And so it can get confusing, but here are some of the other players. There's an argument about coral reefs near the equator. The idea being that as they get warmer and warmer, because of the ecology and interrelationships of the thing, you kill them all off. They all go nuts. They die off in one fell swoop. So that's got a tipping point based on the ecology. Same thing as in the boreal forest. To some extent, the same thing in permafrost. It will conceivably, it will collapse a significant portion of the boreal forest. A gentleman in the hat back here, which of these on this diagram is the tipping point that we're studying? There it is, the medial and our buddy. They've got it placed here rather than up here. It's part of the system. We're focusing on this one. Now there's a color key here, right? What's the significance of the color key, Lady in Black? What is? So so we've got 3 cases, all related to temperature, right? So how is that applied here? Can we find something that threshold where the tipping point would take place, right? And what's an example of a tipping point that requires less than 2 degrees change in order to kick in?
Are you saying for what other tipping point there would be?
Well, this is key to how extreme the temperature change might have to be. So these are all tipping point systems, but an example of one that's less than 2 degrees. I just want to be sure we can read the map.
Low latitude poles.
The low lag, what I already talked about. Another one maybe? Another one is basically the yellow.
And the Greenland ice sheet.
Okay, so the Greenland ice sheet collapse. The concept is that ice sheet might, melting happily at a certain rate today, it might all of a sudden decide to collapse, which would imply a very threshold-like effect. They're suggesting 2 degrees. That seems a little extreme to me. Our buddy requires apparently a 4-degree change. The West Antarctic ice sheet collapse is one of our lessons down the road, so guess what? We're going to get the theme of tipping points again because of this example. And we can talk about sea ice collapse, sea ice being a system. So this is a predicted understanding based on some sort of temperature and how these various things, and they range from permafrost to ecology to the rain, the monsoon, which is part of the ITCZ, to permafrost again, to rainforest, to little glaciers, to big glaciers. So the point is that when you hear about tipping points, you may be talking about different tipping points depending on which system you're up to. We're studying this one today. Gentleman in the suit jacket. Are any of these, have you heard of any of these before? Which ones have you heard of? If you have. If you've not, that's fine.
I would say like the Arctic winter sea ice.
Okay, the Arctic winter sea ice, collapse, Cthulhu. And that's a feedback because of the feedback we talked about, right? The argument is that that feedback could go on, and was that a positive or negative feedback?
Positive.
Say it with conviction, I might believe you, but you put a doubt in it. It is, it's an example of positive feedback. In other words, one that would keep going, keep going, keep going. Now, I also said that in the natural world, most positive feedback systems, which could be catastrophic because they'll break, have some other system that will bring them in control. So there has to be a negative loop someplace if the system's stabilized. And for sea ice, it basically is the fact that it generally doesn't go catastrophic during the annual cycle. The temperature keeps coming back, and so it gets a chance to catch its breath, if you will. But if we get it hot enough, then we could get this catastrophic behavior where it would collapse. That's a pretty big change. We're talking 4 degrees, we're talking the same amount, a little bit close to the same amount of the last ice age. Or not. All right, let's plug along, plug along, plug along. These are a different representation of the same things you just saw. Here's the various things we're talking about. And they're trying to put some quantification on it. And this is the year. So this is something that could happen today. This is going to take a long time to happen. So here's our friend, the Greenland ice sheet. They're arguing here that it's going to take 10,000 years for it to exhibit this behavior. We don't want to hold our breath for that one. We could talk about the Barents Sea sea ice. Well, that one, according to this, isn't going to happen for a while. All of these out here aren't going to happen for a while, according to this, because you need them to kick in longer, basically. The stuff over here is what we're more concerned about, because they have a big magnitude, and they could happen. There's our AMOC. They want to talk about the year 5,000 years. The article you read is closer to like the next 50 years. These are speculations. The point is that different ones of these will kick in at different times. These things could be more dramatic and theoretically, and as you go this way, you worry about them less because they're further in the future. And that's the human psychology. This is the one that they claim is the most sensitive, is one of our lessons, 2 or 3 lessons from now. Anything else we need to know about that graph? All right, I think we're getting almost to the point of an assignment. Oh, excellent. I'll walk through this, I'm going to work through the words and then I'll walk through the graphs. This is a graphic exercise. You're going to make a map. You're going to go back to the exercise we tried to make a convection cell out of the AMOC. We're going to put some numbers on it because we put some numbers on one spot of it. Now we want to put some numbers on a different spot. So the first 3 are all graphic. But this is what you've done before. Get a sea surface temperature, get a salinity, figure out density, plot each one of these on a map. Okay? Leave these for a moment. I'm going to show you. So what we're trying to do is figure out what the water does if we go from the equator up to Greenland. This is conceptual. So I'm giving you a series of maps. Here's the tip of Greenland. This is kind of skewy. This is some scale that's doesn't have any units because it's arbitrary. The same scale in all of these diagrams. There's going to be 3 of them, 3 maps. And what you're going to see here, what I'd like you to plot to start with, is the values. So if we, where are they? There's no scale in this map. How can you do this? You might have to go to this site and find out what yellow is. It's going to be the sea surface temperature. That line's the 28-degree contour. This is 10. That's 28, that's 16. So these are going to be 16, kind of 3 degrees between them. So basically what we want to find is there's 10 degrees, make a y-axis. There's 28 degrees, so we want to make sure that it's high enough to take 28 degrees, and on it goes. So what you're going to see here is a big gradient. This is all similar values. They'll be high, and then it'll drop suddenly and end up with the cold values. And broadly, that's speaking. This is an exercise in actually scaling it off and plotting it. That's for the surface temperature. And if you want the exact numbers, go here. And this one is a different scale. There's Greenland. I've laid it on its side. The equator's basically at the Mediterranean, the equator's here. This one, you're going to have to stretch it out a little bit to get the same 100 meters that was in the other one, that were in the other one. But this is going to give you the salinity. And guess what? Oh, this one's got a scale, isn't that clever? Look at that. 37 of those units. And lower salinity as you come north of Iceland and pick this up. Don't panic about getting that exact color. Get the overall trend. And this one is a different behavior than the other one. This one is more gradational than the temperature. But take 4 or 5 points and then put them back in that ST diagram and then plot them on this thing. Well, there's the ST diagram. So temperature, we don't even go to 28, so that's no fun. And salinity, and say, make a plot of what the density looks like. You already know the answer, I think. I could ask you what you would expect the pattern to be, but let's prove it to ourselves. Okay? Questions on what we're trying to do here? This is the first 3 questions on the, and I'm asking you to put some numbers or diagrams or something on it graphically, and then upload. There's a separate PDF that has just these graphs. So you can just extract that PDF, mark it up somehow, and submit the PDF. Okay? Questions of what we're trying to do though. That was a how to do. Make sense? Okay. Yes, ma'am.
Could you do like an example graph on how to templates or,
Can I do an example graph? So I'm going to draw this as contours. So what I'm going to say, this is a number, and this is, these numbers are not necessarily related to what you're going to do. And this number has 10. This number has 20. This number has 30. This number has 40. Okay? And then on my map, which is the square here, and this axis is simply distance, so you can go from one to the other. So that the 0 to the 100 is no different. Now these units for you are going to be temperature, salinity, and density. So you tell me what you're plotting. We're going to call these hiccups. So these are 10 hiccups, 20 hiccups, 30 hiccups. And so what I would plot on here is I would just kind of transfer this. I mean, here's the map. That's the equivalent of these colors. I don't have that many colored chalks. So I'm going to say this is a tenor. 10 hiccups, 20 hiccups, 30 hiccups, and 40 hiccups. And I don't have any more information, so there's no real point in putting more information on the graph than you have. But that gives me hiccups, or temperature, or salinity, or whatever. And there's subtleties to how the actual values will go as you go from south to north. You're not going to get every one of them. I want you more concerned you wrestle with them. Like this is an interesting one because it's really quite a bit of difference. Over here, gradational color change. Not so much in here. Did that help?
yeah.
More or less, or is that good? Can't have less if you already got it. All right, so if we did hiccups, roughly do hiccups, coughs, and sickness or something, I don't know. Those are the first 3. Separate PDF, mark it up in paint or something, just sketch it on there. There doesn't have to be too. There's a hint in this diagram. And then the second one are more thought questions. This is the key one, obviously. And this is basically the subject of lecture on Tuesday. And to give you a warning, I'm going to give you an example of what had happened, one example. The homework for next week is to go find another example and talk about it a little bit. So you're going to see the same pattern of style of questions from day 1 to day 2 to day 3 every time. So So this is the separate PDF. Now, are there any questions? It's not gonna be exact, it doesn't have to be exact. It's gonna be, you're gonna get frustrated because those two are different scales. But pick, I think what you could do is pick 25 and pick that one. And pick 50 and pick 75 and pick 100, maybe more. And then take those, the temperature and the salinity values, once you get them there, then they plug and chug out of that. Right? You can't do the 28 degrees, it's not on that drawing. It's as much an exercise in creating a different kind of data set than you're used to, actually plotting a different kind of data set than you're used to, spatial data. All right, let's get out of here for the weekend, and we'll see you on Tuesday.